G'day, this is Mr. Thompson. I'm going to show you how to build this spreadsheet which you can use to analyse and in fact design a roller coaster. So given particular track dimensions over here and particular initial conditions and constants up here, we're going to be able to calculate the values, energy loss due to friction, potential energy, kinetic energy, velocity, centripetal acceleration and G-force at any number of points on your roller coaster. Point A, point B, C, D, E, F, G, H, any number of points that you want to calculate. It's a lot easier if you do it with a spreadsheet than it is when you do it by hand. But to work out how to build the spreadsheet and how the spreadsheet works, let's first have a look at how you would do it by hand. Okay, so let's look at this diagram of a roller coaster. We have a roller coaster, well in fact it's a marble, but let's call it a roller coaster, and it starts up here at point A and it rolls down the hill. In fact, this is important, let's say that it starts at point A with zero velocity. So it only has potential energy, it doesn't have any kinetic energy. It rolls down the hill to point B, and we would like to know the velocity and the G-force at point B. Now, we know some stuff. So let's see, what do we know? We know the mass of the ball bearing. You know that because you've measured it on the scale. You know the heights of the height at point A, and you know the height at point B. You know that because you measured those as well. You know the distance along the track, D. You know gravity. Gravity at Westmac is, I think we looked it up, at 9.79 meters per second squared. You know the radius. That's important to calculate the centripetal acceleration. You've got to know the radius of the track at point B, and that's something we'll have to measure, perhaps estimate a little bit, but we'll do our best to measure that from the actual track. And friction, average friction. So in your mini prac, you calculated the average friction along the Hot Wheels track. So you have a value for that. Okay, so if I know all of those and I want to calculate the velocity and the G-force at point B, let's have a look at how we would do it if we were to do it by hand. Okay, so if I know M, G and H at point A, I can work out the total mechanical energy at point A. Now I know that at point A, we said before, we've got zero velocity, which means we've got zero kinetic energy. So all of the mechanical energy at point A must be potential energy. So potential energy is simply M times G times H. You know all that. So you can calculate the mechanical energy at A. So given that, I can find the total mechanical energy at B. The mechanical energy at B is the same as the mechanical energy at A, less the energy that we've lost due to friction. And the energy that we've lost due to friction is simply the frictional force times the distance. So we know the force, that's our frictional force, we know the distance, we can calculate that, we know the mechanical energy at A, so we can calculate the mechanical energy at B. Alright, so if I know the mechanical energy at B, I can find the kinetic energy at B. The mechanical energy at B is the potential energy at B combined with the kinetic energy at B. So if I know the mechanical energy at B, which I've just calculated, and I know I can easily calculate the potential energy at B, it's simply M times G times H, then I can easily calculate the kinetic energy at B. Alright, so if I've got the kinetic energy at B, then I can find the velocity at B. I can simply use the formula kinetic energy equals half mv squared, rearrange that. I can calculate velocity equals the square root of 2 times the kinetic energy at B, which we've just calculated, divided by m, so the square root of all that, that gives us v. So we've been able to calculate the velocity at point B. Now what about the G-force? Okay, to find G-force I need to work out first my centripetal acceleration, and centripetal acceleration is calculated simply by using our formula for centripetal acceleration, v squared on r. So we just calculated v squared, and we know r, or we can measure r, the radius of the curve of the track at point B. Okay, and given the centripetal acceleration at B, we can calculate the G-force at B using the fact that the G-force will be the force of gravity plus the centripetal acceleration. Both of those will be, if you like, pushing us down, and we'll provide a downward G-force, and that'll be in meters per second. If we divide all of that by G, then that'll be the G-force in G's. So that's how we would do it by hand. So this is a spreadsheet that does all those calculations for you, and I'll show you how to build this spreadsheet. So first, let's have a quick look at how the spreadsheet works. So in the spreadsheet over here, over this side, I've got constants and initial conditions. Now those constants and initial conditions remain the same no matter which point we're analysing. So, so I've sort of pulled them out of the table. Now the table down here analyses each point one at a time. So each row refers to a point. So for point A, the distance from the start is 0 meters because point A is our first point on the roller coaster. The height of point A is, well, that's our initial height, which we've actually already put up here. Let me just fix that. Yep. So that's our initial point there. The radius at point A, the radius of the track at point A, our energy lost due to friction. So these fields here that we've just looked at here under the orange banner there, they are dimensions of the track or characteristics of the track. These points, these cells over here are going to be various calculations that we do based on these constants that we know up here, and based on the particular dimensions or the particular characteristics of the track, we can calculate various things. And you'll notice that each of these cells here corresponds roughly, well, it roughly uses the same steps that we just discussed when we were looking at the last PowerPoint. Looking at, we'll calculate the energy lost due to friction, we'll calculate the total potential energy at that particular point. It allows us to calculate the kinetic energy, which allows us to calculate the velocity, allows us to calculate the centripetal acceleration, and allows us to calculate the G-force. Now you've probably noticed already that this first row here is pretty boring. That's just point A, that's at the start, and we've got 0 velocity at the start, so yeah, it's a pretty boring set of values. So what we'll do is when we build our spreadsheet, we'll start building some formulas for point B, and then we should be able to recycle the same formulas that we use for this point. We can recycle them for all the other points as well. So let's get started. Okay, now we've got a bit to do, so I'm going to assume that you know basically how to get around in Excel. So let's let me just zoom in a little bit. So if there are things that I do here that you don't follow, you don't understand, you might have to do a little bit of research yourself on how to operate Excel, or you could come along to my Thursday afternoon tutorial and I can teach you. So let's get started. Let's just put in a heading here, Rollercoaster Calcs. Okay, that'll do. I'm going to bold that, Control B to bold it, and let's just bump up the text size a little bit because that's a heading. Okay, so the first thing I'm going to do is constants. I've got some constants. Enter. So first constant is G, and that's measured in meters per second and let's call that 9.79, I think it is. That's the value at Westmac based on its latitude and its elevation. Alright, let's have a look at other constants we know. We know the mass of the ball bearing in kilograms. We know the friction force. Now you calculated the friction force. I'm just going to put some dummy values in here. You will put the values that you measured. So let me put 0.00105. Okay, let's say that would be 1.05 grams. Friction force, let's say that is, now it was pretty small, 0.00065. Let's make the friction force that size. Now you'll have your own friction force to put in there, so you use yours. Okay, I'm just going to format these. Let me merge and center those cells there. Bold it, Control B to bold, and I'll make all. Let's put a bit of color in here. Make that maroon. I'll make that text white so I can read it. And around the whole thing, let's just put some borders. Some borders, here we go. Some borders, good. Okay, so there are our constants. Now our initial conditions. Initial conditions. Okay, so initial conditions, we have the initial height. Initial height, and that's in meters. So that's the initial height of our point A, if you like, where we're going to start our roller coaster. And our initial mechanical energy, and that'll be in joules. Okay, so let's format that again. Merge and center, color it, bold it, and put some borders around it. Good. Okay, whoops, too many borders. Let's do that. There we go. Good. Okay, now before I go any further, I'm going to name these cells. Now I mentioned this in class. Naming the cells means that when we use autofill later on, these special cells are going to be used in the correct manner. You'll see a bit later on how that works. So I'm going to name that cell there gravity. So not this one here, but the actual data. So to do that, I'm going to select that cell. I'm going to come over here and I'm going to type gravity. So that is gravity, 9.79. So you can see if I move somewhere else, that cell's called C4, but this cell here has a special name. It's called gravity. This cell here, I'm going to call mass. Okay, and this cell here, let's call this cell friction. Friction. Okay, so let's name this one here initial height. Now I can't use spaces in my name, so you can see what I'm doing is click there, I'm just using capitalization. Initial ME, initial mechanical energy. I'm not allowed to use spaces in names. That's a rule that Excel uses. Okay, if you make a mistake and you need to fix any of your names, so you can see all the names here, but you can't actually edit them here. So if you needed to edit any of your names, what you'll have to do is you'll have to come over to the Formulas tab, click on Name Manager, and you can see there are all my names there. So if for example I got one of them wrong, then I could click on there, I could delete it, delete mass, alright, delete it. That hasn't deleted any data out of the spreadsheet. All it's done is delete that name. So if I come here, so I can still see friction, I can still see gravity, but mass, I deleted it. So let me put that in again. Mass. So if you make a mistake, that's the best way to fix it. Okay, so that cell, that cell, that cell, they're all named. Okay. All right, initial height. Initial height, so you'll measure your initial height, or you'll design your initial height, I guess. I'm going to call my initial height 1.007 meters. Okay. And my initial mechanical energy. All right, I'm going to calculate that. So my initial mechanical energy is, now remember we said when we start the roller coaster, the ball bearing has 0 kinetic energy. So I'm just simply going to use the formula for mechanical energy, so for gravitational energy. So equals tells Excel I'm going to use a formula. So I need m times g times h. So m is my mass, equals mass, and then times, and then mg, so times gravity, and then times the initial height. Okay, now can you see how when I selected those cells, it's used the names. So it's actually said, instead of saying equals cell B5 for mass, it's actually used the special name. It's used the name mass. So that sort of makes it easy to read, doesn't it? That's one of the reasons we can use a name, but there's another reason as well, and I'll show you that later. Okay, so my initial mechanical energy is 0.01035. Now that's only a very small amount of energy, and that's expected because we've only got a very small amount of mass. Okay, I might stop this. Alright, the next thing we want to do is record the dimensions of our roller coaster. Well, you're designing your roller coaster, so the dimensions of the design of your roller coaster into a table. So let's do that. Okay, so let's look at track dimensions. Now what we're going to do is we're going to pick key points on the roller coaster. So if we have a look at your roller coaster design, and it should look something like this. We'll pick key points. So point A, point B, point C, point D, point E, point F, point G, point H, my key points. So each row will define the characteristics of one of those points. Okay, so the first thing I want to know about a point is the distance from the start in meters. So how many meters from the start is that point? Well, point A is easy. It's 0 meters from the start because A is the start. Now that heading has spilled over into the next cell. I don't really want that. What I'm going to do here is I'm going to come up to the Home tab and I'm going to click on Wrap Text. Wrap Text. And what that does is that says keep all of that text in that cell. Now you can see it made the cell bigger. I'm just going to adjust that cell size a little bit because I'd rather have it on 2 lines, not on... Let's go a bit wider. Yeah, that's good. I want it on 2 lines, not on 3. Now my row height is too big, so I'm going to double click here. Oh, let's make it a little bit wider, double click here. There we go. When I double click on the cell boundary over here, it right sizes the height of the cell. Okay, distance from start. Actually, I'm also going to center that. Okay, it's being a bit pedantic, but I'm going to do that. Alright, height. We want to know the height of that particular point, and that is also in meters. Now, while I'm here, I typed that wrongly. Let me fix that. That should be friction force in newtons. I'm sure you picked that up. Okay, now you can see I've spilt over to the next cell here, so I'll double click up here and click. It automatically adjusts the width of the cell. Okay, height in meters, and the radius also in meters. Okay, and see I've lost my line there, so I need to adjust that there again. Double click, automatically adjust the width. Okay, let's tidy that up a little bit. I want all of that to be one cell, so I'm going to merge and center. I want to put some, let's put some borders in. Borders, okay, let's center everything. Center, a couple of clicks on center there. Now everything is in the middle of the cell, nice and neat. Our headings, I like to bold those, so Control B, and let's add a little bit of color. A little bit of color here. Let's pick. Let's not go too leery. Let's go with blue. Okay. All right. So everything under here are track dimensions. Okay. I'm going to put some track dimensions in here. Now I'd suggest you just start with your best guess for your design, and once we build the calculations part of the table, you'll see how that design works, and then you'll tweak it later. So bear with me. I'm just going to quickly type these in. Okay, so I've typed these in. Now there's 2 that I haven't filled in yet. You can see I've got the distance from start from every point. So A is at the start, so no distance. B is 2 meters further down the track. C is 3 meters further. D's 3.63, E's 4.26. So my track's an 8 meter long track, 8.26 meter long track. Yours won't be that long, but look, these numbers are just dummy numbers to get started with. Why don't you use these numbers when you build the spreadsheet, and then you can tweak them and adjust them according to your design later. All right, let's have a look. Height. Now height, I haven't actually typed in. You can see height at B is 0, height at C is 0, height at D I've set as 40 centimeters. Back to 0, and then half a meter to G and H. Now height at A, I could type in 1.007, but you know what, I've already typed that in, so I'm just going to put equals the initial height. So whenever I adjust the initial height up here, it'll automatically reflect there. So if I change my initial height to 1.2 meters, for example, there we go, 1.2 meters appears there. Okay, so let's take that back to 1.07007. Okay, now the other thing, I've got to put a radius down here. So at all of my critical points, you'll see at all of my critical points in my track, there is a radius, there's a curve. The only point that I haven't got a curve on is point H. It's straight. What am I going to do there? Now, one of my formulas, I need to divide by the radius. So my formula for centripetal acceleration is v squared divided by r. So I don't want to put 0 in there, and in fact 0 wouldn't make sense anyway, because if I had a 0 radius track, that would mean an infinitely small circle, which I haven't. I've got a flat. So what I really should have is an infinitely large radius, which would make it flat. I can't do infinitely large, but I can do 99999. Let's do that. So that's such a large radius. In fact, let's not do quite that. Let's go there. Yeah, that's such a large radius that it's not going to make any difference to our calculations, and it won't cause a divide by zero error in my calculations later on. Okay, so hopefully you've got yours in there as well. So let's look at what we want to do next. So the next thing I want to do is my calculations based on those dimensions. So calculated values. Let's do that. Okay, first thing I'm going to calculate is my energy lost due to friction. Energy lost due to friction. That's going to be in joules. Now I want to adjust that a little bit. Make that a bit bigger, and I'm going to wrap the text. Beautiful. Okay, so that fits on 2 lines. That's exactly what I wanted. So I'm going to calculate my energy lost due to friction. How do I calculate that? Let's come down to B, because A is sort of a bit of a trivial case. Let's go from B. The energy lost due to friction. Now, the energy lost due to friction is simply, well, it's the work done. It's negative work that's done by friction. So how to calculate the energy lost? It's going to be equals, it's going to be the force, the friction force, which is this up here, friction force times the distance. So the distance we've travelled from the start is 2. So what that's saying is between the start of the roller coaster and point B, we've had a frictional force working over a certain distance. So F times D is the work done, and work done is the energy lost due to friction. So hit enter there. So that tells me that I've lost by the time I get to point B, I've lost 0.0013 joules of energy. Okay, that's my first calculation. I want gravitational potential energy, and I want that to be in joules. So at point B, what is my gravitational potential energy? Well, it's going to be m times g times h. So equals, m is my mass, that's a constant up here, so I click here, there's my mass, times g is gravity, so I'll click up here, times h. Now what's h? H, my height at point B is 0. Okay, mass times gravity times height. If I hit enter now, 0. I've got 0 gravitational potential energy at point B. Okay, that's good. I expect that because when I'm at 0 height, I should have 0 gravitational potential energy. Okay, my next calculated field. I'm now going to calculate my kinetic energy. Kinetic energy in joules. Okay, so to calculate my kinetic energy in joules, well, my kinetic energy is simply the energy that I started with minus the energy I lost due to friction, minus any energy that's been converted into gravitational potential energy. Okay, so let's do that. Equals, so my kinetic energy is the energy that I started with, that's my initial mechanical energy, minus the energy that I've lost along the track so far, minus any of the energy that's been converted into gravitational potential energy. So in this case, no energy is gravitational potential energy. But let's put the correct formula in, because we're going to use this same formula for all the different points, and some of the points do have some gravitational potential energy. Alright, so I've now calculated for point B, now I've got my kinetic energy at point B. Alright, once I know my kinetic energy, I can calculate my velocity. My velocity in meters per second. Meters per second. Enter. Okay, that's gone ugly as well, so I'm just going to right size the cell. I'll double click up here. Alright, the formula for velocity. So if I know my kinetic energy, then I know that kinetic energy equals half mv squared. So if I rearrange that, I should get my velocity equals the square root. So squirt, that's an Excel function, open brackets, the square root of 2 times kinetic energy, there's kinetic energy, divided by mass, there's my mass over there, close bracket, enter. there's my velocity, 4.152212606. Way too many decimal places, but we'll fix that later. 4.15 meters per second. Terrific. Okay, one more thing I'm going to calculate here. I'm going to calculate my centripetal acceleration. So Excel's painful with subscripts. Let's write AC. Now I'm going to come up here and I'm going to select just my C and convert my C into a subscript. So if I come to font, click on more font options down here. Hello. Here we go. And I'm going to change my C to a subscript. Okay. All right. Enter there. That didn't work. Let's try it again. Font to a subscript. Subscript. Enter. Okay, that's got it. All right. So centripetal acceleration, and I need to make that in meters per second and it's been painful. Okay, let's select meters per second. Go to font again and make that so it's not subscript. Okay, and finally we've got that right. Okay, so centripetal acceleration in meters per second. Maybe it would have been easier just to write centripetal acceleration. Anyway, we got there. Okay, so the formula for centripetal acceleration is v squared on r, velocity squared divided by the radius. So this is where we need the radius. So equals v squared, that's v, and if I use caret 2, that means v squared, and v squared divided by r, so divided by my radius. Enter. And there's my centripetal acceleration. That's a pretty big centripetal acceleration, 34 meters per second. The reason it's so big is because we've got a reasonable velocity, 4.4 meters per second is a reasonable speed, and we've got a very tight corner. If you're in a car and you try to turn a corner that was 0.5 meters in radius, that would be a very, very tight corner. Here it's a ball bearing, so in a real sized roller coaster we wouldn't have a corner anywhere near that small. So what we will find is because our roller coaster is small, our centripetal accelerations are going to be very, very large. In fact, when we calculate the GForce, it's enough GForce to squish you probably, but our roller coaster will be a real roller coaster would be a lot bigger, so you wouldn't have such a tight GForce. Okay. That will do. I'm going to leave the GForce column till later because the GForce formula varies depending on whether it's an inside loop, whether it's a loop, a concave or a convex, or whether you're upside down or right side up. I'm going to leave you to do that actually. I'll give you some notes and I'll give you some instruction on that in class, but I'll leave you to do that final column with GForce. There we go. So I'm not going to do the calculation there. I'm going to leave that for you. All right, let's format this. Calculated values. I want that merged and centered. Very good. I want that blue. So let's do that. I want that bold. So Control B. Around all of those, I'm going to put some borders. Okay. Hopefully getting quite quick at this. Now, I've typed all those formulas in once. The cool thing about Excel now is I can take all of those formulas and I can drag them. So if I autofill like this, so what I'm doing is I'm grabbing this little box down here with my mouse, dragging all the way down, and I've autofilled. Terrific. Okay, so what I've done is now if I look at each formula, let's go to cell, let's go to this cell here for point E. If I hit F2, okay, you can see the formula for F2 is friction. Because I actually used a named range for friction, it hasn't actually used the cell, one of the cells under that cell. It's actually kept using that cell, whereas this cell here has come down. As I've auto-filled these cells here, it's referencing the cell just to the left of that cell. Okay, so this cell here was friction times B15. When I auto-filled, this cell here then became friction times B19. So hopefully you can see now why naming the cells was so useful. Okay. All right, we've got a couple of problems over here. We've got a number problem and a number problem. Now, why would that be? That's because here our kinetic energy is negative. what does that actually mean? If our kinetic energy is negative, now you can't have a negative kinetic energy. What really has happened is our calculations here are saying that H is too high. It's too high. The ball bearing would have never got to H, so that's why it's negative. So if we increase the initial height just a little bit more, then what we should find is that'll change all our calculations, and we should have some positive kinetic energy, which you can have. So let me change that. Instead of 1.07, okay, so I've gone to a height of 1.1. If I go to a height of 1.1 there with these values, you can see that we do now have a velocity. So you can see the velocity as we've gone through the track has gone 4.5 meters per second, 4.2 meters, 3 meters, back to 4 meters per second, 3.8, 1.6, 1.2. Terrific, that looks good. Okay, now we haven't completed the first row yet. I'm just going to take that row there, the second row. I'm going to autofill upwards again. There we go, we've got our first row. Alright, congratulations if you're still with us. This has been a marathon effort. Okay, one more thing I'm going to do. These numbers here are fairly clumsy numbers. We've got lots of zeros in front, and we've got way too many decimal places. Actually, let's fix these ones easier. These ones here first. So, too many decimal places. Let's change that. So if I click here, number, we'll click number, and we'll go, let's go to 2 decimal places. I think that's reasonable. So if I click OK, there we go, 2 decimal places there. That's much more sensible. All right, now these ones here, these really should be, they're such small numbers, they should be in scientific notation. In fact, better than scientific notation, better if we put them in engineering notation, which is I guess it's a type of scientific notation where the exponent is always a multiple of 3. So it's easy to tell whether it's millijoules or microjoules, rather than having something by 10 to the minus 4 and have to sort of reconvert it in your head. Anyway, let's do it. So I've selected all of these cells here, and I'm going to format them. I'm not going to give you too much explanation, but just follow along. First, I'm going to go to scientific. So I'm going to start with scientific notation with 2 decimal places. Good. Now, having used that as my default, I'm now going to come to custom. So if I come to custom, now you can see this is the code for scientific notation. It's like the template, if you like. That's the standard sort of format for scientific notation. What I'm going to do is I'm going to come over here and I'm going to put 2 hashes, hashtag, if you like, in front of that scientific notation. I won't bother explaining it, just do it, you'll see what happens. Okay, now you can see, actually we've got a few hashes here, that just means it doesn't fit, so let me just right size that cell, okay, make it bigger, there we go. Alright, so all those zeros just mean 0, but here we go. 1.3, what this means is 1.30 by 10 to the minus 3. So you can see all the exponents here are by 10 to the minus 3 or by 10 to the minus 6. So that's nice because that means 1.3 millijoules. And this one here means means 798.7 microjoules. The 10 to the minus 6 tells us micro. So that's a nice notation to use when we're doing engineering. Looks a bit messier, but I think that's a little bit more elegant. Okay, that's it. So now you've got your spreadsheet. Now you're able to play with all your conditions here. Play with your what happens if I have a height of 1.5 meters. I've just redone all my calculations. Terrific. What if I have I don't know. What if I make my final height, what if I make it 0.8 meters? 0.8 meters. Okay, what happens there? What happens if I make it, in fact, what happens if I make my height 1 meter? Let's come back to here. My initial height is exactly 1 meter, and my end height is 0.8 meters. I get these nums again. What does that tell me? That tells me my ball bearing won't actually make it that high. So as you can see, you can play around with your parameters here and it'll automatically recalculate all your data points. So a much more powerful way of doing it than with pen and paper. Let's put it back to 1.5. All right, that'll do. Well done for sticking with this long and arduous video.